Welcome to The Explainer. Today, we're going to do something that I think is truly fascinating. We're going to take this tiny but incredibly powerful computer, the Raspberry Pi 5, and show you how to run some seriously sophisticated modern applications on it. We are talking about building a system that really mirrors the architecture of the big-time cloud, but right here on your desk. Okay, so let's just frame the core problem we're trying to solve here. Imagine your project starts to get bigger. You're not just running one simple script anymore. Suddenly you've got a web server, you've got a data processor, maybe something reading from a sensor, and they all need to run at the same time. The real question is, how in the world do you keep all of that running smoothly without them just tripping all over each other? So here's our roadmap for this. We're going to start by really digging into the problem, and then we'll explore the modern and honestly super elegant solution. After that, we're going to get our hands dirty with some actual code, package it all up, and then for the grand finale, we'll launch our very own miniature cloud system. First things first, let's unpack this challenge, because this is a hurdle that pretty much every developer hits the moment a small project starts to become something bigger. I want you to picture this. Your web server needs one specific version of a software library to run, but oh no, your data processor needs a different, totally conflicting version of that same library. All of a sudden, your entire project just grinds to a halt. This, my friends, is what we call dependency hell. And trust me, it is a very real and a very, very frustrating problem. But there is a powerful, modern way to solve this. So let's introduce the two key concepts that are going to completely change how we think about building applications, especially on a device like the Pi. So instead of building one giant, clunky, monolithic application, I want you to think of building a team of highly focused specialists. You've got one service that just handles logging data. You have another one that only does user authentication. Each one does its one single job perfectly, and it does it independently from all the others. That is a microservice. Okay, so how do we manage this team of specialists? Well, we do it with Docker containers. The best way to think of a container is like a perfect, self-contained box for each one of our microservices. It packages up the code and all of its dependencies together, which guarantees that it's going to run exactly the same every single time, no matter where you put it. And the difference here is, it's night and day. On the left, you've got the old way, this big, tangled ball of code, where a single little failure can bring the entire system crashing down. But on the right, you have the clean, resilient microservice approach. In this world, if one service fails or maybe just needs an update, the rest of the system just keeps on chugging along. All right, theory is great, but let's make this feel real. We are going to build a system with two distinct microservices, a little team of two specialists that will create a simple but really powerful data logging application. Let's meet the first member of our team, the data logger. Its entire purpose in life is to listen for incoming information and just record it safely. You can think of it as the system's memory. So we built it using a super fast, modern Python framework called FastAPI. And it's simple. It just waits patiently for data to be sent to its /log web address. It's specifically looking for temperature readings. When it gets one, it slaps a timestamp on it and writes the whole thing to a file. Simple, focused, and totally effective. Now for our second specialist, the sensor simulator. A logger is pretty useless without any data, right? So this service's job is to create that data, basically pretending to be a real-world sensor. It runs like clockwork. Every 10 seconds, this script just wakes up, generates a random temperature, and then sends it straight over to our data logger. This is the heartbeat of our system, constantly feeding it new information, exactly like a real hardware sensor would in an IoT project. So we have our code for both of our specialists. Now we need to put each one into its own perfect, isolated little box. It is time to containerize them using Docker. So how do we do that? We use a special file called a Dockerfile. Honestly, the best way to think of it is as a recipe. It's a list of every single ingredient and every step that Docker needs to build the perfect environment for our code to run in. Everything from the base operating system to the final command that starts our app. And you know what? The recipe is usually this simple. First, we start from a base image, in our case, a lightweight version of Python that runs great on the Pi. Then we copy our code into it. We run a command to install its specific dependencies. And finally, we give it the CMD or command to execute the moment it starts up. With that recipe, our Docker file, all written, we just execute a single Docker build command. Docker reads our instructions and perfectly assembles a self-contained, runnable package that we call an image. We'll build one for our logger and a separate one for our simulator.
Okay, this is it. This is the moment we've been building up to. We have our 2 specialists, and each one is packaged neatly in its own perfect container. Now let's launch them and watch them start working together as a team.
So now that they're all packaged up, how do they actually find each other? I mean, instead of messing around with complicated IP addresses, Docker gives us a much more elegant solution, a private, virtual network that's just for our containers. With one simple command, boom, we create a little bridge called EdgeNet. Now, any container we connect to this network can find any other container on that same network just by using its name. It's kind of like giving them their own private, secure phone line. Okay, time to launch. First, we start the data logger and we connect it to our EdgeNet. Now, this next part is absolutely critical. We use a V-flag to create something called a volume. This links a folder inside the container to a folder on our Raspberry Pi. So why do we do this? Because containers are temporary by design. Without this special link, our log.txt file would completely vanish forever if the container stopped. This makes our data persistent. Then we launch the simulator on the exact same network and we just tell it that the logger's name is data logger. That is it. Docker handles all the complex networking stuff completely automatically. So, did it actually work? Well, the proof is in the data. Because we saved our log files safely outside the container, we can just use a simple Linux command to peek inside that file and see what our data logger has been up to. And there it is. Look at that. Inside the file, we see time-stamped temperature readings, one after another. This is our proof. The simulator is generating data. The services are communicating across their own private network, and the logger is saving everything to a permanent file. Our 2 independent microservices are working together as a single, coherent system. That is a success. And look, what we've just built together, this isn't just some little toy project. This idea of separating concerns, this containerization, this service-to-service communication, this is exactly how massive, scalable applications are built in the cloud. We've just gone and done it on a Raspberry Pi. So the real question now is, with this kind of power, what incredible things are you going to build?